Okay, we can start. Welcome everybody. Good morning. Last time we were playing with the script when we stopped x1 ur5 task space control.py. So you can reopen this one and also the configuration file, which is x1 ur5 reaching conf, and we can restart where we left. So as a first thing, I'm gonna just run the script to see where we left. So we were doing control of this robot manipulator in task space, so controlling the position of the end effector, which is this orange sphere, and the red sphere represents the desired position, which is moving on a circle or, well, circular shape. And we had already played a bit with the hyperparameters because in the beginning there were very high frequency switches from maximum to minimum joint velocities, which we didn't like. And so we managed to make that a bit better by reducing the gains, I think. Somebody suggested that. So that has improved indeed. Of course, we are asking the robot to reach a configuration, so a point with the end effector that is impossible for the robot to reach. So the tracking is not going to be perfect. We can see that we have some errors here at the peaks in the x direction. We are still getting some of these high frequency oscillations. So I would try to make them go away. I mean, if I had to transfer this motion on the real robot, I wouldn't want that. So any idea what else we can change except, of course, lowering again the gains? Because lowering the gains, of course, is going to help. And I mean, just for seeing, we can test what we get by lowering the gains. Yeah, this is much better. You can see that there are no high frequency oscillations in the motion. And I mean, the joint velocities now are very smooth. So we no longer have these jumps that go from minimum to maximum very abruptly. So everything is very smooth. So this is a motion that could go easily on the real system. So that's nice. But why I'm not satisfied with that? I think you can already see it here. With respect to the tracking we had before, how is this? Yeah. So now we have tracking errors even in the bottom part of the plot. Before, at least, it was tracking well until like 0.8. So everything that was below 0.8 was well tracked. And we only had the errors in the upper part of the sinusoid. Now we have them everywhere. And this is a simulation with a perfect model. So again, a very ideal situation with respect to reality. If we start introducing modeling errors, this is going to become worse and worse with such low gains. So on a real system, you cannot afford such low gains if you want good tracking. So this is not a good solution. I think we should go back to the gains we had before. And 10 is still quite small, I would say. There is another parameter we can play with. The weight of the task. Yeah. Yeah, that's it. So here we have the weight. We have one weight for the end effector task and one weight for the postural task. And of course, if we increase too much the weight of the postural task, which now is 10 to the -3, we're going to deteriorate the tracking of the end effector task because the two tasks are in conflict. You cannot track a fixed joint posture and a moving end effector trajectory. These two are incompatible. But I think we have room for increasing a bit this weight, because now it's 10 to the minus 3, which is quite small. We can try to set it, for instance, to 10 to the minus 2. And that should help stabilizing the motion of the robot, because basically that's a task that is asking the controller to maintain the robot fixed. Let's see. It is helping. So these are the joint velocities. And again, we got rid of the high frequency oscillations. So that's good. And the tracking now is better, because we got back to something that was more similar to what we had before. So in the bottom part of the plot, we have good tracking, and we only have like significant errors in the upper part. And that's kind of the best we can ask in this case. We cannot really ask to do anything better. So if you have taken another class on robotics, and you've studied methods for doing Cartesian space control with the Jacobian pseudo-inverse, you can think of the weight that we are using here for the postural task as having an effect that is very similar to the damping of the pseudo-inverse, if you know what that is. So when you take the pseudo-inverse, you can either take like a standard pseudo-inverse, but almost nobody does that, or you can dump it numerically. So you can add some regularization to this pseudo-inversion. So the regularization weight that you add to the pseudo-inversion is having the same role as the weight of the postural task here. So it's basically helping you avoid very high joint accelerations in this case, which are linearly proportional to the joint torques. So the higher you set this one, the smaller are going to be the joint accelerations. We can try to set it too high to see the effect it has. So if I set it to 10 to the minus 1, it's probably too high. So now the motion is even smoother, but the tracking is pretty terrible. So it's very smooth motion. Okay, this is very like smooth sinusoids now we have in joint space. But if you look at the tracking of the end effector position, now it is deteriorated. We can see we have large tracking errors both in the upper part and in the lower part of the plot. It is very delayed, the motion. And this is a trial and error approach. I mean, you cannot know in advance what is going to be the right weight for this task. You need to try a bit. Luckily, we have simulators, so it's pretty effortless to try. You just change the gain, you run it again, you look at the plots, and when you're satisfied with the overall behavior, you typically transfer it on the real system. So I would go back to the gain we had before, sorry, to the weight we had before, 10 to the minus 2. Another thing we can play with here is joint friction. So far we haven't introduced joint friction. We can add it as we did before last time for the joint space controller. So I set to 1 this flag, simulate Coulomb friction, always in the configuration file. And then I can introduce some Coulomb friction, maybe 2. So the Coulomb friction is going to be equal to 2% of the maximum torque at that joint. And I can see how that is going to affect the behavior. Of course, it's going to make the tracking a bit worse, or a lot worse by looking at it. And we can clearly see the stick and slip behavior even at the end effector, looking in the viewer now. So everything is very smooth still. But this is the behavior at the end effector. And we have the sticking phase, slip phase, sticking phase, slip phase, and so on and so forth. Tracking is definitely much worse than before. So how do we make it better? Yeah, same old. So increase the gain. Let's go big. We set it to 100. Try again. You can see it's a difficult task for the robot. It has really to struggle to get it. So now, I mean, for sure, the end effector tracking is going to be better, but we are also getting some of these rapid changes from maximum to minimum velocity in joint space. They are not super bad, so they're not as rapid as they were before. We can see here we have some time. There is some slope, it's not a vertical line. And at least I don't have 2 or 3 of them in a row. It's just once. So maybe this is acceptable. We can go and look a bit closer. Yeah, so this is like happening in half a second, so it may be okay. These are the joint torques. A bit more shaky than they were before. This is the effect of the high gains on top of the Coulomb friction at the joints. But on the plus side, we are tracking better now, despite the Coulomb friction. So not perfect tracking, but better. But we don't see anymore the stick and slip, because the gains are sufficiently high to basically always overcome the stickiness of the induced by the Coulomb friction. And I mean, now we're asking for a motion that is very demanding for the robot because it's outside its workspace. So this forces the robot to go always in singularity. The singularity is when the elbow is completely stretched. So you have a straight arm. And that's a very difficult configuration for a controller because the Jacobian loses rank. And so it tends to produce very high joint accelerations. If we were to make the motion a bit simpler, like here, reducing the amplitude in the x direction to 0.1 instead of 0.2, probably everything would be better. So I'm still struggling quite a lot. But the plots are better. I mean, now the transition here is taking longer. Joint torques seems a bit better than before. And the factor, also this one is a bit better than it was before. Again, not perfect. And this error that we are seeing, I think it's mostly due to the Coulomb friction. I think if we run the same test without the Coulomb friction, we should get perfect tracking. Doesn't seem we do. Since nothing has changed, I guess we also have to set this one to 0. Why? Bug? Yeah. Yeah. Now it's more like it. Yeah, now we can see the difference. So joint velocities are good, joint torques are good, and tracking in the end effector space, good. So all the errors we were seeing were due to the joint Coulomb friction, which unfortunately is a very frequent, very real phenomenon. So you see it in most robots. Its magnitude may vary, of course, depending on the hardware, but it's something that you almost always have. Okay. Of course, you could still go nuts with it and play with different parameters. Like you could have the motion in the YZ plane instead of being in the XZ plane by changing the amplitude here. See, now the motion is happening in this plane. This one was an easy trajectory for the robot to track. So we see that everything actually goes very smoothly. You can play with the joint velocity limits, joint torque limits by changing these two parameters here, which are scaling the limits of the robots to make it more or less challenging for the robot to achieve the task. You can change the initial configuration here. You can change the controller frequency, the simulation length. You have many options to play with, but I'm not gonna stay here and play with all of them. I'm just listing them so that if you want to understand better how these kind of controllers work, well, here you have the option to do so. So I would stop here for the coding part of today. Do you have any question on that? Good. Then we can move on and we can start talking a bit about optimal control. So since we are done with the first module of the course, which was the one on reactive control, soon I'm gonna give you the first assignment, first homework. That's gonna consist in basically writing some code to play with one of these reactive control methods. And then you're gonna have to answer a set of questions, write a short report, like a couple of pages typically, and submit it to me through the website. So I'm typically giving you 1 week or 10 days to do it. If for some reason you have some other assignments at the same time and that seems to be too short, you can ask me for more. We can go up to 2 weeks if you want. It's not a problem for me. So these assignments are mainly there to motivate you to get acquainted with the material during the semester, not waiting until the very end to start playing a bit with the codes and understanding the theory. And as a bonus, you get very easily 3 points for the exam, because every assignment is worth 3 points out of 30 of the total mark at the exam. So there is also that extra bonus. Okay, we're going to talk more about the assignments later on. So before we start discussing about the theory of optimal control, I wanted to show you a few videos of what you can achieve with optimal control. But let's start with a very basic question. What is optimal control? Well, optimal control is a family of methods for doing robot control, or actually for controlling any dynamical system. So everything you're going to learn here about optimal control, of course, in terms of application, we're going to focus on robotic applications, but the same techniques can be applied also for controlling many other kind of systems, like chemical plants, or you can control autonomous vehicles. You can use it even for like applications in economics. So anytime you have a differential equation describing a dynamical system and you have some control inputs for controlling this system, you can apply optimal control basically to that problem. It may be or not the best tool for solving that problem, but it is an option. And very often it's a very valid and powerful option. So it dates back to the 17th century, and the first problem that was solved with this kind of techniques, it's a very simple problem. You have a ball that starts from a point A and has to reach a point B subject to gravity. So gravity is pushing downward. And the question was, what should be the shape of the terrain connecting point A to point B that makes the ball reach point B in the minimum time? Okay, you can imagine you might have like a linear slope here connecting point A to point B, and the ball just rolls down the slope. Or you might have a slope that goes down very quickly and then it's almost flat. Or you could have anything in between. What is the shape that leads to the fastest motion from point A to point B? This question was asked by Bernoulli in 1696, and by using optimal control, an optimal control approach, he was able to get an answer, which is the brachistochrone curve. It's a curve that looks like that. It's a red one. And as you can see in this animation, it's the one that leads the ball to reach point B in minimum time with respect to the other options. Of course, here we are seeing only 3 options, but I think that's proves the point. I would never have said that this was the best one out of these 3, but it happens to be. Of course, since the 17th century, optimal control has made some progress, so now we are able to answer questions that are much more complex than this one. So in general, optimal control can be used to answer questions such as how can we accelerate a car to reach a given goal in minimum time, so solving minimum time problems. How can we accelerate a car to reach a goal with minimum energy? That's also another very common option. You want to minimize energy. Or how can we reach a goal with maximum speed? So every time there is a metric that you want to optimize, so either minimize or maximize, that's the same. Optimal control is a very good tool for getting such behaviors out of your system. We are going to see some examples then that are more specific to robotics later on. So the way an optimal control problem is written down is very similar to how you write down an optimization problem. So you have a cost function to minimize, and then you have a set of constraints. The first one is typically the model of the system, so the differential equations that describe how the system evolves in time. So in the case of a robotic system, those would be the dynamics of the robot, the one we have already seen, the mq double dot plus h equal tau. Those are the differential equations that describe how the system evolves in time. But then on top of that, you might have any constraint that you want. And constraints are super, super useful in robotics because robots are subject to many different kinds of constraints. You have joint position limits, joint velocity limits, joint torque limits. You have self-collision avoidance, avoiding collision with the environment. And then you can add any other constraint that is specific to your application. So let's see some examples of motions that have been generated using optimal control. These are actually now quite old results, but I think they still prove the point. So how to walk at a certain speed while ensuring balance. This was a 2010 result with a humanoid robot called HRP2. It's a Japanese robot. And these people were able to achieve a walking behavior using optimal control. And what's even more impressive is that in this case, the robot is receiving commands from a joypad that a human operator is using, and the motion is computed in real time. So the robot doesn't know in advance where it should go. It just receives these commands from the joypad, and it computes online the motion and then executes it. So this card here is just there for safety reasons. It's not doing anything. So the strings here are loose. They're not sustaining the weight of the robot. And this was 15 years ago. Here is another result, a more recent one, 2017, a more complex behavior. In this case, the robot was tasked to climb the stairs, but it's not sufficiently strong to do it without the handrail. So it also has to use the arms to pull itself up a little bit. Here is an application with a robot manipulator, if I remember correctly. Yeah. So the robot has to move this bottle through this opening, but the problem is that the opening is too small, so it cannot pass, maintaining the bottle straight, so it has to tilt it. But if it tilts it too much, then of course friction is not sufficient and the bottle falls over. So the only way to achieve this task is to make it dynamic like this. So you have to pass through the opening with some velocity so that the bottle sticks there and it doesn't slip over. And this again was computed using optimal control. Here's a different application with drones. If it starts, probably it won't. Yeah, it didn't. Here's another application, again, a humanoid robot. This one is in simulation. Again, optimal motion computed online in real time. So there is nothing pre-computed here. But and the main difference with respect to what we have seen before is that now the robot is making contacts with all its limbs. So you have contact with the hands and with the feet, and you don't know in advance which limb you should use to make contact. So the robot is deciding, it's taking this decision automatically by solving an optimal control problem. It's kneeling down to avoid the collision with this high bar. This was an application that was instead proposed in computer graphics, but it's very similar to what one would do in robotics. So you have these simulated avatars that have to produce realistic motions. And indeed, they produce motions that are very realistic. And this is extremely difficult to do. So this was not in real time. This required offline computation. But the quality of the motion is very impressive. And here the main complexity comes from the part that the robot has to decide all the contact patterns. Nothing is predetermined by the user. Everything is automatically discovered by the optimizer. You see it's using both the hands and the feet in a very irregular way. Here's doing some climbing. Here physics is not completely satisfied because the goal of this work was more to produce like beautiful motions to look at more than transferring it on a real robot. But I think it's pretty impressive, and it made an impact also in robotics, this work. Also some collaborative task between two avatars. In this case, the task was to reach this height, and they figured out that the little guy should climb on top of the big guy to achieve this height. So pretty advanced motions. So that was it for the videos. We can now move on to the slides. Yeah.
How much time was needed for the last video?
I'm not sure if that was reported exactly in the paper, but for sure we are talking about at least minutes. So maybe tens of minutes of computation. So it's not at all meant to be a real-time motion generation. But those are very, very complex motions to generate. So I think it's reasonable that it takes minutes.
And a way to incorporate the results in a real time, I mean, like pre-computing and then recognizing a set of motion that can be used in real time.
Yeah, I think that can be done, and it actually has been done recently. So I'm bad at multitasking, so I'm gonna take care of the blinders and then answer. So yeah, more recently, actually, there are people who are who have been achieving this kind of very complex motion generation in real time, where the solver is taking care of figuring out which contacts to make and to break, and generating the whole motion of the robot, and doing that in a like model predictive control fashion. So it's a real-time optimal control. However, I've heard by talking to the people who did it that it's very challenging to do that. So the overall framework is quite brittle, and it needs a lot of careful tuning to work correctly. I mean, even that offline motion generation, many people have tried to reproduce it and failed miserably. So it's not something that's easy to achieve, even if possible, because of course we have proof that somebody did it. So it's possible, but still very hard.
You upload. I think they're not public yet.
Yeah, you're right, because I had uploaded them only until the last one. So I'm gonna do it right now. It takes me a second. They're gonna be slightly different from the ones that you're gonna see today, but I'm gonna update them as we go on. So let's start by comparing optimal control with reactive control, which is what we have been discussing so far in this class. So in reactive control, we have seen that we need a reference trajectory to track, or a reference fixed state that we want to stabilize. And basically the controller is taking care of tracking that trajectory. So that might be good enough for certain applications, like if you are in an industrial setting and you know exactly what trajectory the robot should track, then probably you're good with the reactive control. And typically in reactive control, the performance of the systems may be specified if you use classic like linear control tools. You might have metrics such as rise time, overshoot, settling times. You might have encountered these terms if you took any class on classic control theory. They might be good for certain applications, but the main limitation of reactive control, classic reactive control, is that it's very hard to handle constraints. And even if you look at the more advanced reactive control methods, like the ones we have been seeing recently, so the QP-based control methods, where you're using an optimization solver inside the controller, and so you can handle some constraints. So we saw that we can handle joint velocity limits, joint torque limits. We could even handle friction cones or contact forces. But other constraints are very hard to handle with those tools, such as joint position limits. We have seen that they're hard to handle. And collision avoidance constraints. We haven't discussed much about them, but they're very hard to handle with reactive control methods. And the reason why they're hard is that in reactive control, you're only looking at what's going on right now at this very moment in time. So you're reasoning in terms of accelerations, contact forces, joint torques, and that's it. If you want to handle like position constraints, either at the joint level or at the Cartesian level, like we're doing obstacle avoidance or self-collision avoidance, reasoning only about what's going on right now is not good enough. You need to look into the future, look at how your positions are going to change into the future, because you need to start taking action now to avoid something bad happening in the future. So that's the examples that we did also when reasoning about joint position constraints. If you want to avoid hitting your joint position limit, you need to start braking maybe half a second before. You cannot wait until you're this far from the limit to start braking, because at that point it's too late, and whatever you do is, well, you're cooked. So that's the reason why typically reactive control methods struggle with this kind of position-related constraints. And then enters optimal control. So in optimal control, the situation is very different, because now we no longer need a reference trajectory in general. Of course, you can also work with a reference trajectory in optimal control. That's not forbidden, you can do it, but it's not strictly needed, contrary to reactive control. What you need instead is a cost function. So you can specify any metric, any cost function that you want. That's typically going to be a function of your state and your control inputs of the system. And the solver is going to find a motion that minimizes that cost function. So it's going to be optimal for that cost function. So you can generate like minimum time motions or minimum energy motion or maximum speed motions, whatever you want to optimize, just put it in the cost function and the solver is going to minimize it or maximize it. And I think the most important aspect of optimal control is that it can handle constraints. Any kind of constraints that are functions of state and control can be handled. So all the constraints that you can handle inside QP-based reactive control, you can also handle in optimal control, but you can also handle more advanced constraints, such as joint position limits or collision avoidance. I think those two are the most important ones for robotics. Yeah, here we had an example of what rise time and settling time were. So rise time was the time for the system state to reach like 90% of the target value, and settling time was the time needed for the state to start remaining inside a tiny window around the reference value. And overshoot is by how much you overshoot the reference value. So this could be metrics to be used when you're doing classic control. So optimal control with respect to reactive control is going to be much more powerful in general, because it allows us to generate motion in a much more flexible way and more complex motions. Of course, the price that we'll have to pay for this increased power is also increased complexity. So computation time is going to be higher. That's the main disadvantage. But for today's standard, I think computation time for optimal control is still very reasonable. So you will see that we will be able to generate motions quite fast, even at interactive rate for doing control in some cases. Let's see how an optimal control problem may look like in math. So OCP, those are the initials for optimal control problem. I'm going to use them a lot, so memorize that. This is the optimal control problem. And you can see it at a first sight, it looks a lot like a standard optimization problem. It's very similar. You have a cost function here that you want to minimize. These are your decision variables, X and U, so the state trajectory and the control trajectory. And then here you have a bunch of constraints. The first constraint represents the dynamics of the system, so the so-called equations of motion. And that typically comes in the form of a differential equation, x dot equal f of x ut. So how the state evolves is a function of the state, the control inputs, and maybe even time. For a standard robots, there is no dependency on time. So the dynamics of the robot is independent of time. So my robot today moves as it moved yesterday. But in general, you can have time-varying dynamics. You typically have fixed initial conditions, so you know the initial state of your system. It's not mandatory. You could also have problems where the initial state is free, but most of the times the initial state is fixed. And then you have inequality constraints, very general function g of x ut that represents physical limits of your system, such as joint torque limits, joint velocity limits, joint position limits, collision avoidance, and you can add whatever you want on that. The cost function is composed of two terms. The first one is called running cost, and the second one is called terminal cost or final cost. The terminal cost depends only on the final state, x of capital T. Whereas the running cost is an integral of a function that depends on state, control, and time in general. So you integrate this function throughout the whole trajectory. And the trajectory in this problem has a fixed length, which is capital T. So this must be fixed by the user. And notice the dynamics constraints and the path constraints must hold for the whole duration of the trajectory. So for every time between 0 and capital T. So at first sight, this looks like an optimization problem, but it's not an optimization problem. It's not a standard optimization problem. There are a couple of crucial differences which makes this way, way more difficult than a standard optimization problem. First problem, the decision variables of this problem are state trajectory and control trajectory. So since they are trajectories, they are infinite dimensional objects, because a trajectory is a function from time to some space. So either the state space or the control space. And since it's a function, well, you cannot represent an arbitrary function with a finite amount of numbers. So there is no like finite dimensional parameterization for representing a function. So this is not equivalent to a standard optimization problem where your decision variables are some vectors which have a finite dimension. This is an infinite dimensional decision variable basically you're working with. And that's a first issue. Second issue, the constraints, they must hold for every time in a given segment in a given window, which means also the constraints are infinitely many, because you have infinitely many time instants between 0 and capital T. Okay, time is continuous, so you have infinitely many time instants, which means you have infinitely many constraints. And that makes this problem different from a standard optimization problem, where instead you have a finite number of constraints and you have finite decision variables. Okay. So the first challenge that we will need to deal with exactly is this one. How do we go from this formulation, which is very nice and general, but is untractable in practice because it's not something that we can take as is and pass to a solver and ask for the solver to find a solution. We need to work a bit to make it tractable. But before we do that, let's see an example. Let's see a very simple example of what an optimal control problem might look like for a pendulum. So we have this object here, this robot, which is a pendulum. So we have just one joint, one rigid body attached to this joint that can rotate about the joint. And we want the pendulum to do the classic swing up. So go from whatever position it's at to the top position and stay there stable. And let's say that the top position corresponds to a 0 angle. So we want Q equals 0. Let me erase this. So the optimal control problem is going to look like that. Let's start from the constraints. The first constraint is always the system dynamics. In the case of the pendulum, the system dynamics is nonlinear, and it looks like that. We have the inertia of the body about the rotation axis of the joint, I, times the acceleration, Q double dot. It's equal to the joint torque plus gravity. And gravity in the case of the pendulum looks like that. So we have the mass times gravity, so 9.81, times the sine of the joint angle, Q. Why is this nonlinear? Yeah, so this is the only nonlinear term we have, but that's enough to make the whole equation nonlinear. So if this system here is nonlinear, you can imagine that all robotic systems are nonlinear because you cannot go simpler than that.
Can you repeat why there is identity of
It's not identity, it's the inertia. This is a scalar. It's not a matrix. So everything here is scalar because it's a 1 degree of freedom system. So this is the inertia, which is going to depend on the inertial properties of this body. Okay. So this is a quantity that you know. It's going to be 3.82. Then to work in an optimal control framework, you typically want to write down the dynamics as in standard form. So in this case, we have to define what we are going to use as state of the system. Well, for almost all robotic systems, the state is the stacking of the joint configuration Q and the joint velocities Q dot. So we just stack basically positions and velocities together, and that's the state of the system. Whereas the control input U are the joint torques, tau. And then we can write this equation here in standard form. The standard form is x dot equal f of xu. So x dot, well, if x is q dot, we take the derivatives of those. We have q dot, q double dot. And then this is equal, well, q dot is equal to q dot. There is no dynamics there. Whereas q double dot is equal to this expression here. I just moved, no, I didn't move anything. I just multiplied everything by the inverse of the identity. Yes. I don't know why there is a minus there, it should be a plus. Okay. It's just a rewriting of the same expression in this like vector form, because you need to specify the dynamics for all your whole state. But I did nothing complex there. Okay, so we took care of the dynamics. Then we need to fix the initial state. So we know where the robot is now, what is its state when we begin. So we fix it. So Q at time 0 is equal to some value, Q init, and Q dot at time 0 is equal to some value, Q dot init. Those are going to be constant. And then we can add any physical constraints. Typically, we are going to want to add torque limits, because the motor at the joint is going to have a limited amount of torque it can generate. So we set that. We're gonna have joint position limits. So the joint position must be within certain limits. And maybe we can add a terminal constraint to say that the state, so the joint angle at the final time t must be equal to 0 if we want to make sure that the robot reaches exactly the desired joint angle, which is 0. This is a choice, a modeling choice. It's not a physical constraint. And then we have also the cost function to work with. So the cost function, we know it's an integral between 0 and capital T. And then we can decide what we want to add inside that cost function. And here it's where you come in, basically, because up to this point, everything was kind of textbook. But now when it's time to define the cost function, you need to decide what you want to add there. And depending on what you add in the cost function, you're going to get a different motion. Okay, so what can we add in the cost function? Any idea? The joint angle. So okay. Squared always. Squared.
Where else we got forks?
You could also have the torques, yeah. And now we can weight them, yeah. So these two terms in practice are very similar.
So that the
Yeah, okay, let's discuss a bit the running cost first. So these two terms here are going to be very similar because torques and accelerations are linearly dependent. So as you make the torque higher, you're also making the acceleration higher. So in general, I would either minimize the torques or the accelerations. Minimizing both feels a bit redundant, but could be done. It's not a problem. And that's going to result in having torques that are a bit smaller and also smoother. Maybe that's not trivial, but typically when you minimize the square of a quantity, which is a trajectory, that also has the effects of smoothing it out. It's not only going to reduce the peaks, but it's also going to make it smoother, which is very good for robotics. This, of course, is going to have the effect of making the the joint trajectory is a bit slower, because if you're minimizing velocities, it's going to be slower. Maybe it's less obvious what this is going to do. No, that's not it. What is this gonna do in the resulting motion? So if we have this terminal constraint here, we know that the pendulum is going to reach 0 anyway.
Maybe shorter path to zero.
The fastest, I would say. It's going to make the pendulum reach 0 faster, because this is an integral cost. So we are summing up all the values of Q along the trajectories. So it's not only a matter of reaching 0, but we want to reach 0 as fast as possible, because the sooner we reach 0, the sooner we stop accumulating this integral cost. And anytime we are not at 0, we are paying some extra costs, because we are adding this Q square to the cost. So having Q there is basically like asking the solver, not only I want you to reach 0, but I want you to reach 0 as fast as possible. Okay, and the higher this weight, the more important that request is going to be with respect to the other request. Because here we are asking the solver to do several things at the same time, and these several things are incompatible with each other. You cannot have minimum joint velocity and minimum joint position and minimum joint acceleration and minimum joint torque. Okay, if you just have one of these terms, you're gonna get a completely different motion. They are not compatible. So here the weights are gonna be super important for getting the motions that we really want out of this solver. Of course, if you just, for instance, minimize the joint velocities, what is the optimal motion? It just stays where it is. And that's not the motion that we want. So this weight here is going to be small, because otherwise the robot is just going to stay still. So this weight is going to be much, much smaller than the others, for instance. Actually, the same goes for these two. If we really want to minimize joint torques or joint accelerations, well, the best thing to do is not to accelerate, not to apply any torque. But that's not what we want. We want to reach the terminal state. And maybe we want to do it also as fast as possible, which is going to require some high velocities and some high torques and high acceleration. So here we are asking conflicting things, and the trade-off between the different objectives is going to be determined by the weights. So you, as the designer of this optimal control problem, are in charge of finding the weights that lead to a good behavior, good according to your taste, basically. And then we have the terminal cost. The terminal cost must be a function only of the terminal state. So I think that here the only thing that makes sense is something like that. So this is a capital T, even if it's not maybe super clear. So I'm adding a penalty for the terminal value of the joint angle and joint velocity. Of course, that only makes sense if I don't have this. Because if I have a terminal constraint that Q at time capital T must be equal to 0, it doesn't make sense to penalize the value of Q at time capital T because I know it must be 0. So penalizing it is useless. It's going to be a 0 penalty anyway. So these are alternative options. I can either have a constraint or I can have a terminal cost. And of course, if I have a constraint, I'm going to be sure that at the end, the robot is going to be exactly at Q equals 0. If it is a terminal cost, it may not be exactly at 0. Maybe it's going to be at 10 to the minus 3 or 10 to the minus 2. I don't know. It depends on these other terms here. So again, that's a choice for you to make.
So if I don't have a Q of T equals 0, I need the...
You need the terminal cost. Yeah, you need either this or this. The same goes for the joint velocity. So you could have either here Q dot at capital T equal to 0, or you could have it here as a terminal cost. It depends how much you care about this. If you really want to achieve that with a very high accuracy, then use it as a terminal constraint. If it's more something like, I wish that would happen, but it's not the end of the world if it doesn't, then you put it as a terminal cost. Another option that you have as a designer is not to use like squared penalties. You can have other kind of penalties which are non-quadratic. For instance, you could have linear penalties, something like this. You could have the absolute value. And the same goes for the running cost. You could use absolute values instead of squared values. That's a valid choice, and it actually has a different effect on the motion. So in general, if you have a squared penalty, basically what you're saying is, I really want to avoid large values because by taking the square of it, that is heavily penalized. So for sure, you're going to avoid large values if possible. But when the error is small, the squared penalty makes it smaller. Because if your error is 0.1, well, you take the square, it becomes 0.01. So you are actually much more tolerant to small errors with a squared penalty, and you're very intolerant to large errors. Whereas if you use an absolute value, it's the other way around. So it's going to try to push the error really to 0 because it has a constant slope. So even when you're at a small error value, the gradient of that error is still going to be the same as it was when the error was huge. However, squared penalties are much more common in practice because they are smooth. So they are differentiable everywhere. If you use an absolute value penalty, then it's a bit trickier, mathematically speaking, because you have a point which is at 0 where the function is non-differentiable. Because on the right it grows, and on the left it also grows, and so you have different limits coming from the right or from the left. But solvers can typically deal with that quite nicely, so it can be used. And there are some tricks for making this actually differentiable everywhere. Just to show you that when you're writing down an optimal control problem, you're deciding what terms you want to have in the cost function, in the constraints. There is a lot of choices that you will need to make. And one of my objectives for the coming weeks is actually to teach you how to make those choices and understand the consequences of these choices. So I think we have been going on for more than 1 hour. and I can tell that from your faces. So let's take a break. I'll see you back here at 53. So we saw what an optimal control problem is. We saw an example of it for a very simple system, a one-dot pendulum. Now, when it comes to solving optimal control problems, there are plenty of techniques available. And here I'm showing you a taxonomy of optimal control method families, which are categorized depending on whether they are global methods or local methods, and whether they work by first optimizing and then discretizing, or the other way around. So let's start first by discussing the difference between global and local methods. I think the name is pretty intuitive. Global methods are methods that try to find a global solution to the problem. So the global minimizer for the given optimal control problem. And that's a very ambitious goal. So in general, it's super hard to find the global solution of an optimal control problem, unless, of course, the optimal control problem is convex. But in robotics, forget about convex problems, okay? The system dynamics is nonlinear, so you don't have a convex problem, period. So finding global solutions, extremely hard in general. Local methods instead are less ambitious. They're more pragmatic. They try simply to find a local minimizer to the problem. So a solution such that by moving locally, you cannot improve. In general, a local minimizer might be terrible compared to the global minimizer. So you don't have any guarantees on the quality of the solution that you're going to find with a local method. But in practice, it happens that very often that's good enough for practical applications, okay? So in robotics, actually, local methods are much, much more common than global ones. Then we have the other two, the columns. And here the difference is in the order in which you perform these two operations. So typically when you have an optimal control problem, which is this infinite dimensional optimization problem, you have two operations that you need to take care of. One is the discretization, which is basically the process that allows you to go from an infinite dimensional problem to a finite dimensional one. You approximate these infinite dimensional variables and these infinitely many constraints with a finite number of variables and a finite number of constraints. That's basically the discretization. And you have the optimization. So once you have a finite dimensional object, you optimize. Well, it happens that you can do these operations in either order. You can do discretization and optimization, or you can do optimization directly working with these infinite dimensional objects, and then you discretize later. So depending on which order you choose, you get different optimal control methods. Okay, so by working with this two-dimensional taxonomy, you can divide the spectrum of optimal control methods into these four classes. So global methods, if you work with first optimization and then discretization, what you get are the so-called Hamilton-Jacobi-Bellman methods, which are based on the Hamilton-Jacobi-Bellman equation, which is a partial differential equation. Whereas if you work by first discretizing and then optimizing, the class of methods that you get are the ones called dynamic programming. You might have already encountered these two terms in other classes. If you've taken any class on optimal control or motion planning also, you might have encountered these two families. So dynamic programming is actually at the foundation of many also reinforcement learning methods. So we are going to discuss dynamic programming later in about 1 month when we start discussing reinforcement learning, because we're going to start from dynamic programming algorithms as the foundation for then deriving reinforcement learning algorithms. Let's move on to local methods. Again, you can divide local method in 2 classes. If you go for the first route, so optimization first and discretization later, you get these methods here that are known under many different names. So indirect methods, or Pontryagin maximum principle, or calculus of variations. These are terms that are used to refer basically to the same class of methods. And I'm not going to discuss them in this course, also because there is another class taught by Professor Bertolazzi, who is discussing these methods here. So I don't think that's I need also to cover that topic. And also because in robotics, these methods are not very commonly used. So since our main focus in this course is robotics applications, we don't need to worry about these methods here. What is very, very much used in robotics are the direct methods. So we're going to focus on those in this class. The idea behind direct methods is very simple, very pragmatic. You take an optimal control problem, you discretize it. So you take the optimization variables, which are infinite dimensional objects, these trajectories, you discretize them by introducing some parameterization. You do the same for the constraints, because you have infinitely many constraints. You just discretize them in time so that they become a finite number. And then what you get is an optimization problem. It's a standard optimization problem, so you can use a standard numerical optimization software to find a local solution. Period. That's the idea of direct methods. That's why they're called direct methods, because you're directly taking the problem, discretizing it, solving it. It's a very pragmatic approach, and it works very well in practice, and it's very flexible because it allows you to deal with any kind of constraints. So you can have inequality constraints of any kind on the state, on the control input. You can just put them in there, and they, well, they should work under some conditions. So yeah, the next lessons are basically going to be focused on direct methods. They're very simple as main idea, but there are some caveats that we need to be aware of, because there is not a single way in which you can transform an optimal control problem into an optimization problem. There are some choices that you need to make, which come with pros and cons as usual. So the idea is going to be, well, to show you these pros and cons, both in theory and then in practice when we're going to implement these different transcription methods. That's how they're called. The problem, the process of going from the infinite dimensional problem to the finite dimensional one is called transcription. We're going to see different ways we can do that and how that affects the practical performance of the solver. But before we go into direct methods, I actually want to take a quick detour and discuss a little bit how optimization solvers work. Because as I told you, direct methods basically transcribe an optimal control problem into an optimization problem, and then they just give this problem to a solver. So if you don't know anything about how a solver works internally, then this will remain a black box, and it's going to be very hard for you to debug problems when they're going to arise. And trust me, they're going to arise, because a solver is not a silver bullet. So it can solve problems only if they are formulated with certain constraints. So we will need to be a bit aware of how the solver internally works to be able to use it in a good way. And especially each solver has some hyperparameters, as all algorithms have. And so you need to understand the meaning of these hyperparameters so that you're able to tune them depending on the behavior that you see. So the first thing that we're gonna study is numerical optimization algorithms. Who has taken some class or at least some lectures on numerical optimization? Be a bit more proud of that. Raise your hand. Okay, so very few people, maybe 5 people. And I mean, by that, I mean that you know like gradient descent, Newton method, KKT conditions. Okay, I see only one person nodding. Okay, so yeah, that is needed because most of you don't know what that is, and that's kind of important for working with optimization solvers. So we don't have much time left, but we have some time. So I've prepared a notebook to try to make this quite lightweight and interactive. So let's start from the very basic of numerical optimization. Let's say that we simply want to minimize a function, f of x. This function, we're going to assume it's differentiable. So we can use gradients. That's a kind of a big assumption, but it's super important because all the optimization we're going to talk about in this course is going to be gradient-based optimization. So we need to have functions that are differentiable at least almost everywhere. So like the absolute value function, which is differentiable everywhere except at 0, that's acceptable. It works in practice. But you cannot have functions that have discontinuities everywhere because then we cannot use gradients. But again, in robotics, there are in many applications, this assumption holds in practice, so it's fine. Or we can introduce some approximations to make it hold even when it doesn't hold for real. So this function must have a multidimensional input, but a scalar output. So it's a function that outputs a single scalar value, but it can take as inputs as many variables as you want. So the input space is typically Rn, where n is anything. So in optimal control problems, it's going to be something like 100 or 1,000 variables typically. So if this function is differentiable, then it means that it has a gradient. And the gradient is going to be a vector. And each element of the vector is the derivative of the function with respect to one of its input variables. So the gradient is going to have the same dimension as the variable x. So it's going to be an n-dimensional vector. And typically the assumption is that you can compute these gradients quite efficiently. So it makes sense to use it because it's efficient to compute and it provides you lots of information about the local behavior of the function. So how the function is behaving around the point where you compute the gradient. So a very simple idea for finding a local minimizer of a function of which you know the gradient is simply to follow the negative gradient direction. Because you know the gradient points to the direction of maximum increase of the function. Since we want to minimize, well, we want to go exactly in the opposite direction with respect to where the gradient points. So that generates the simplest gradient-based optimization algorithm, which is called gradient descent, which works like that. You start from an initial value for the variable x, which is your so-called initial guess. If you don't have any initial guess, typically the solver uses 0 as initial guess. It's a valid choice. And then you iterate. You have an iterative algorithm where at each iteration of the algorithm, you evaluate the gradient. So nabla f evaluated at the current guess, so xk. And you simply modify your current guess by moving a little bit in the negative gradient direction. So your next guess, xk plus 1, is gonna be equal to xk minus eta times the gradient. So this value eta is a scalar value, positive, which you need to define, and it's typically gonna be quite small. This is what is called the learning rate in deep learning, more general machine learning algorithms. And that's going to be, of course, a critical hyperparameter of gradient descent. So we can imagine that if eta is sufficiently small, at each step of this algorithm, actually the function is going to decrease. Because the gradient we know that the gradient gives us a good approximation of the function in a neighborhood that is sufficiently small. We don't know how small. Well, if the function is linear, then eta can be anything. It's just going to work because the gradient is a good it's a good approximation of the function actually everywhere, because it has a constant gradient everywhere. In general, of course, the function f is not going to be linear, and so we will need eta to be sufficiently small, and how small depends on the function. So it's a tricky parameter to tune automatically. But it's a starting point for doing gradient-based optimization. So let's see how this works. And let's start simple. Let's start with a simple quadratic function. So let's suppose that the function f is simply x minus 3 to the power of 2. So it's a squared function. It's convex. So if we were to plot it, it will look like a bowl. It has one minimum, which is, of course, both local and global. And the gradient of this function, well, in this case, it's a one-dimensional gradient, simply a derivative, is 2x minus 3. I think we are all set for this one, right? So we can write a simple Python code which implements gradient descent for this very simple function. So I've defined the function here using this lambda expression. Is just a way to define a function in one line. So the function is x minus 3 to the power of 2. This is the gradient, is 2 times x minus 3. My initial guess is x equals 0. And then I'm going to iterate the algorithm for 20 times. I do 20 iterations. And at each iteration, I subtract from my current guess of x eta times the gradient of f. That's exactly the same expression that I wrote above, but implemented in code. And then just for logging, I append the current value of the guess x to this list, which is called history. So that later on I can see all the iterations of the algorithm. And then I just do plots, basically. I plot to see what is going on. I hope that works. Okay, it does work. Okay, so here you can see two plots. The plot on the left shows the function f of x, which is a quadratic function, so of course it looks like a bubble. And I can see in red all the values of my iterations. So in this case, the learning rate was set to 0.1. And I can see that I started here from x equals 0, where f of x is equal to 9. And then at each iteration, I moved on towards the minimum, which is at x equal to 3. And in 20 iterations, I was there. So this worked. On the right, I can see the value of the function f plotted against the number of iteration. It's in logarithmic scale, so I can see how quickly it's going to 0. And we can see that we are starting from the value 9. And we are going down linearly, but in logarithmic scale, which means that we're going down exponentially, actually. And in 20 iteration, we reached almost 10 to the minus 3. So we are not really at the minimum, which would be 0, but we are quite close to it. And if we wanted to get closer, well, we would just need to increase the number of iterations. So instead of doing 20, I can do 30 iterations, and I can rerun this. And in 30 iterations, we are almost at 10 to the minus 5. That's quite accurate for robotics applications. I could have also been satisfied with 10 to the minus 3, to be honest. Of course, we had to get the learning rate tuned right. We can change it. So what happens if we make the learning rate smaller? I can see that. So let's say we make it 10 times smaller. It's 10 to the minus 2 now. It's still converging. It's just much slower. You can see that now in 30 iterations, we haven't reached at all the minimum. So we are actually here. Well, we can also see it in this plot. We are roughly at 2 point something instead of being at 0. So the learning rate, if you tune it too small, well, it's going to slow down convergence, because at every iteration, we make very, very little progress. So even if we go in the right direction, it takes ages to get to the minimum. So we need to be careful with that. So in this case, it's not too difficult to get a good learning rate. So yeah, I would say that roughly at 0.06, the convergence starts to be sufficiently fast. And then let's see how high we can go. We can go very high, actually, and it's still gonna work. And you can see now the precision that we got is super high. So now we are at 10 to the minus 29. But if we go too high, you can see here at 0.5, there is something that starts happening. So before 0.5, all the red points are on the left of the minimum. But then when we pass 0.5 as a learning rate, we can see that we start seeing some red points on the other side. And then we start seeing this phenomenon of overshoots. So what is happening here is that as we iterate, we go from this point to this point, and then from this point to this point. So every time we overshoot a little bit. We are still converging, and the final result is very good. We are at 10 to the minus 23. But we see this overshooting. And as we increase more and more, the overshooting gets worse, and the final accuracy gets worse. You can see that we went from 10 to the minus 25 to 10 to the minus 9 or minus 10. And at a certain point, this is gonna break, of course. So now the accuracy is getting very bad. 10 to the minus 2. So 0.97, 0.98, 0.99. And when I set the learning rate to 1, I have no convergence. I'm just in a infinite loop where the value actually of the function doesn't improve at all. Because I'm jumping from this point to this point and then back to this point, and I keep iterating between these 2 points forever. So I'm stuck in a loop. And what happens if I make the learning rate even larger? Then instead of converging, actually the algorithm is diverging. Because at every time I go a bit higher. So I'm overshooting way too much. Of course, this will never happen if I were to use gradient descent on this function, because I would never set the learning rate this high. It's a crazy high value for a learning rate. Typically, a learning rate is much smaller than 1. So I will probably never go above 0.1. And we saw that if we stay below 0.1, the algorithm works beautifully on this function. But just to show you that in general, the learning rate can break the algorithm if you set it too high, and it can make your algorithm super slow if you set it too small. So you need to be able to tune it, especially if you use standard gradient descent. Let's see now something a bit less trivial. So let's try to optimize another function. She's always quadratic, but this time it's a 2-dimensional function. So we have 2 input variables. I call them x and y. And we can see that there is one variable that has a coefficient that is much, much larger. Well, it's 100 times larger, which is not much by numerical standards. But it's sufficiently larger than the other to make this problem interesting to look at. So I've implemented the same code as above, just for a different function, which is in this case 2-dimensional. So when we compute the gradient, now the gradient is a 2-dimensional array. It's not a scalar anymore. And also the variable x is a 2-dimensional array. And I'm starting from this value 1.5. The algorithm is the same as before, and then I'm doing some plots. Okay, and this one was supposed to be somewhere else. So let me just fix that. And then we can run this. Okay, it didn't like it because I think I broke it somehow. And I need to call the function. So 0.05. Okay, so you can see that in this case, actually the algorithm doesn't work. So on the right, we can see the same plot we had before. So we can see the value of the cost function as the number of iteration increases, and we can see that it's not converging, it's actually diverging. So the function didn't seem that bad. It's a quadratic function, it's convex, and the learning rate we are using is again not crazy, it's 0.05. So I'm not using a learning rate of 2, which is of course too large. This is a reasonable learning rate. So it could work, but it doesn't. And to make it work, we will need to make it smaller. So in this case, we can see that it's making progress by setting it to 10 to the minus 2, but it's not super satisfying because it's making progress very slowly. And we can see what's going on in 2D space. So what you're seeing here are the level curves of this function. And we can see that this function, even though it's quadratic, the level curves are not at all circular. They are very narrow ellipsoids because the curvature in one direction is very different from the curvature in the other direction, which makes this valley very narrow. And gradient descent is really struggling because it's jumping from one side to the other of this valley here. So actually, to make it work, we will need to go much smaller in terms of learning rate. So now it's working better because it's not jumping from one side to the other side of the valley, but it's still making progress very slowly. So it's making progress quite fast at the beginning because it's able to go from here to here, and that comes with a lot of progress in terms of value of the cost. But then to get to the minimum of this valley, it's actually taking ages. You can see that the slope of this curve at this point, which corresponds roughly to the point where the iteration got into this area, the slope is now really smaller than it was before. And with that, we run out of time. So we're going to continue this notebook on Friday. See you on Friday.